Okay, good afternoon. Let's go through the basic principle of cardiac CT. I'm going to try to make it more clinical rather than a lot of science. You know, that's a lot of physics, but we'll try to make it clinically applicable. Okay. So someone tell me what's the problem with this patient? So this is a cardiac CT, and here we diagnose a patient with rupture of the distal LAD after the Lima graft. This is the 4D images. So we're going to talk about how do we get to image like this to help the patient. Okay, let's see. All right, this is the timeline of cardiac CT development. As you can see here, X-ray has been around for a long time. So instead of a stationary chest X-ray tube and then project toward a patient and end up in a film, CT is a little bit different. CT actually you send an X-ray through a patient and you have a detector on the other side that rotates through the body, so it allows you to do tomographic imaging. The possibility of doing coronary CTA did not happen until in late 1990s, where 16-slide CT was available, And that was the first time we have enough temporal resolution and enough coverage to reasonably freeze the coronary. And you can see since that time till now, there's been an explosion. Okay, if you look at this, in 2000 we have 8 slices, 2002 we have 16 slices. Now we're talking about 620 slices, 640 slice CT, and we have photon counting CT. And I'm not even going to mention the amount of clinical data that's been amassed for the last 10, 15 years. I think that's unique in terms of non-invasive cardiac imaging. Okay, so this is a basic. I don't know what happened. Okay. Okay, so CT scanner use a case, a donut hole casing, and within that donut, actually, it's hidden inside. It looks nice and friendly and smooth and relaxing, but inside there's a lot of machines and detectors. So you have something that rotate around the source of X-ray, rotate around the patient. Patient goes to the middle. And what makes things rotate is the gantry. So that's, okay. And then X-ray emit photon, goes through the patient, and the signals is detected and picked up in the detectors. So you could have a single source, that's the majority of the CT. Dual source CT is what we have here for cardiac application, where instead of one source, you have 2 sources. So since you have 2 sources, you have also 2 detectors, okay? So this is where things happen. Okay, so what is the general process to getting a CT image? So this is very basic for any CT, okay? First, we need an X-ray tube to generate electrons and then photons, okay? So different from nuclear. Nuclear is emission, SPEC is emission tomography, correct? Because we inject radio tracer and patient heart is the one who's sending the signal. So this is transmission. Transmission meaning that I'm sending the energy or the photon externally, go through the patient and get detected the other side. Okay, so the main thing, because SPECT is also CT, but it's emission computed tomography. Okay, so that's the difference between SPECT and regular CT. So you generate this photon. We can talk about how we generate later. Go through some collimator so we can focus on the patient sitting here, laying here in the middle. And this thing's going to go around the patient constantly in synchrony with the detector. So detector, so you acquire the data, so detector, then traditional CT use a photodiode tube to convert the photon into electrical signal. And then in the computer, that's why it's called computed tomography, because you rely on computer to do a lot of calculation. And that's the origin of the name computed tomography. So you have a lot of mathematical process, essentially convert the attenuation or whatever, essentially convert a number into images. Okay, this is obviously, we have a conference yesterday just talk about this, and obviously because the audience here, we don't need to go into too many details. So I'm going to focus on things that would be important for you to understand when we mention some of the terminology of CT. So first, we need to generate photon to go through the patient. So essentially what we do, we apply heat to cathodes, right? When you have generate enough energy, some of the particle from the surface of this metal is going to release electron. That's how an electron is going to be attracted going to the anode. And this process will release X-ray because of the material we use. And that's called thermoionic emission. So basically, this is how the photons are generated. okay? And depending how much energy we apply to that is completely controllable by you. You can determine what the maximum energy you want, okay? So this is, so remember this part. So this is the part we acquire the images. Okay, so after we acquire the images, each X-ray goes through the patient's body, come out with attenuation number, and everything is number. And through filtering, which essentially what we do is we pick up the signal with high frequency because it gives us better picture and get rid of some of the lower frequency one. So it's to get rid of the blur, and that's what the filtering does. Okay, so this process of reconstruction is convolution of this CD data into images. I say it real easily, but this is a very complicated mathematical process. So the key here is a very important part of the image you're going to see, because you're going to determine what kind of filter you use depending on what kind of structure you want to look at, okay? And now we're going to introduce the terminology, because from the X-ray tube that I show you, you can send out, okay, I want certain amount of X-ray photon. So, and that's called tube current. You can program it, okay? So it's proportional to a quantity of photons. So more current equals directly proportional, more radiation and better image quality, okay? Because you're producing more signal. And what we usually express is MAS, which is a product of tube current multiplied by millisecond. Okay? As you can see here, right in the middle has less MAS compared to the one on the right. Okay? So the image quality is better contrast. And this looks a little more grainier. Okay? So if you want better image quality, you can give more MA. Okay. So if you have a patient who is obese, you know, size matter and size increase noise. And basically, you have to increase the MA. And if you increase twice the MAS, you have 40% increase in the signal noise ratio. This is just another example. In the left-hand side, we use 650 kV MA versus 800 in the right-hand side. And thinner slices versus thicker slices, as you can see. It's more grainy, but you see more detail compared to, you see more contrast and edge detection, but you kind of lose the granularity of the, for instance, this, the trabeculation or pop muscles, not pop muscle, trabeculation. So basically, it's a trade-off, because if you want to look at the coronary, you want to look at the plaque in detail, you probably want to be thinner slices. But if you want to look at myocardium, I mean, thicker slices will be fine, okay? So we talk about number of photons that you want to control. Now we talk about energy. So we use the term KVP, go for peak kilovoltage. So more energy you give to that X-ray tube, higher the energy, the photon that come out. So when we apply this, it's a maximum voltage apply. Okay, so therefore, the highest kinetic energy of the electrons that produce photon is never going to be more than 100, whatever you apply. They say, if you put 120 kV, the spectrum of X-ray that you generate is never going to be more than 100 keV, okay? So it'll actually be lower. So this is key sentence here. So kilovolt is a voltage that you apply across the X-ray lamp that generates the keV to go for electron volts. So KV is what you apply to the tube. And KEV, spectrum of KEV, is what you get after, because you don't always get exactly the same, but usually it's always lower than the peak KV. Okay? For instance, if you give 100 KV, okay, typically you get a range of from 15 KeV. KeV go from the energy of the spectrum of the X-ray, 15 to 100, and average is usually it's about 1/3. So if you give, let's say, 70 KV, most of the KeV you're going to get is going to be around 30 or 40. That's why we use low KV, peak KV, to get to lower KeV, similar to what is the KV of the iodine. So you get more contrast. Okay? So you can see here, that's the main difference that I want you guys to understand. So KV, you have control, right? In KeV, what's generated, you can kind of, it's very standard, so you can expect what kind of energy spectrum that you're going to be seeing after you apply that KVP. Okay? As you can see here, it's similar, right? I mean, if you have higher KVP and lower KVP. Okay? So lower KVP, you're going to see more noise. You're going to see more granularity. 140 kV essentially looks smoother. Okay? So again, this is depending on the patient habitus and structure you're looking for, you choose the maximal energy. So it's not one size fits all. Okay? But routinely we use between 100 to 120 kVp. So, but our scanner allows you to dial from 70 to 140, I believe. Not every scanner has a capacity. Okay? So as I mentioned earlier, if you use lower KVP, you would detect the iodine better with better contrast to noise ratio than higher KVP. Okay? So this is just an example of using 120 kV versus 90 kV. So lower kV, closer to the edge of the iodine, you get more signal. Okay, you can see it's a little bit brighter, right? So essentially, if you use lower KVP, you can improve the image contrast for the angiogram, but you increase noise and less image quality. So for a thin patient, it's probably okay, but for an obese patient, the noise will be so much that you won't be able to interpret, for instance. But if you want to look at the myocardium only, it's probably, again, that level of noise is acceptable. This is one important concept that is probably going to show up in your board exam, essential implication and radiation of choosing your tube current and choose your tube voltage. Okay? So tube current, as I mentioned earlier, is directly proportional. So you increase the MAS from 500 to 600, you're giving the patient 20% more radiation. Where if you give tube voltage from 100 to 120, that's 20% increase in the kV to the square. So you increase the radiation by 44%. And that's something that you need to consider in mind. Sometimes if you want to do trade-off, you could keep the same kV and just increase the MA, for instance. Okay, so that's the first step. We generated the KV, and we generate the X-ray. Now X-ray is going to go through the patient, okay? So what we look at here is interaction between the photon and X-ray with the tissue, okay? So attenuation coefficient, that's what we call, that's actually what we're detecting, reflects the degree that X-ray intensity is reduced by certain type of tissue material. As you can see, denser material, more going to be stopped. Okay? Just by convention, we use the Hounsfield unit because this is one of the guys who pioneered CT. So by convention, is 0 be this style of water in certain standard temperature and atmospheric pressure will be 0. And air will be minus 1,000. So that's basically the convention, okay? Anything else could be in between. So anything denser than water is going to have positive Hounsfield unit. Anything less dense than water, you're going to have negative, okay? So in a way, I mean, this is a very crude tissue characterization, right? Because if you look at this chest CT, very dark, that's air, okay? Oh. There's bone, going to be positive. There's a little bit of contrast, going to be positive. And this is soft tissues, going to be, depending, it's a lot of fat or not. So, and this will be epicardial fat, will be negative, like around minus 100. And soft tissues around 100 to 150, okay? And that's why, for instance, it's very useful CT to look at calcification, like this patient. With this, there's no other thing could be other than calcium, what you're seeing here, okay? Same here, for instance. This is a patient that has lipoma of the RV. You can measure the Hounsfield unit is around minus 100. There's no other thing. It's fat for sure. There's no other thing that could have similar Hounsfield unit. Here, for instance, we know for sure it's soft tissue. So I know this pericardial thickening is neither calcium, neither fat, it's soft tissue. But I cannot tell, for instance, here without any contrast, because the blood and the muscle has similar attenuation, so I cannot tell them apart. That's why we give contrast to help us characterize the tissue in a way, okay? Just another example here, circular coronary, so you can. So the implication is CT is capable to a certain degree for tissue characterization, very specific for air. So if you see air anywhere, for instance, air in the, occasionally we see that when we inject contrast, you see air bubble in the right atrium, right? And we know that's air for sure. Water is also very specific, fat for pericardial effusion, fat and calcification. But again, not for soft tissue, at least not yet. Okay. So again, so we talk about the X-ray tube. We send the X-ray through the patient. So the patient tissue and body attenuate your photon. So now we go to the detector, right? Remember what I showed you earlier. So the detector, what does the detector serve? Besides capturing the signal, it determines the slide width and in a major extent to spatial resolution. Because if you have two detectors, it's very thin, and they are separate detector, you can tell the signal could come from different place, allow you to see the separation of two points, okay? So essentially, thinner the detector width, better the spatial resolution. But the problem is you can only make it so thin, right? You cannot, because when it becomes so thin, each one going to receive very, very small signal. So actually it's going to be very noisy. So you need to give more kV or MA. So overall, when you have more slices, you have better spatial resolution, but the radiation, to keep the same image quality, the radiation dosage is actually higher. Okay? obviously that's not the only thing that determines, but that's one of the major limitations. And that's what we're going to see later on, what other thing we can make the improvement. Okay. So when we do coronary imaging, we want always the thinner resolution, right? The best spatial resolution. But remember, this is about cardiac CT. So if you want to look at the myocardium, if you look at single slices, you might not have enough signal to detect, for input hypoperfusion. So actually, you want to give a larger thickness. Okay. So when you reconstruct the image into a slight thickness, it really depends on what you're looking for. Okay. But for our practical purposes, for coronary imaging, we want thinner slices, and that generate noise, and because the less signal, so usually you have less contrast resolution, but you have better edge definition. You get more detail, right? Versus all the contrary, like here in the bottom part. We increase the thickness, and this looks easier to read, but because you have better low contrast resolution, but you lose detail. Okay. Okay, so the other major differential characteristic of CT compared to other imaging modality is what we call isotropic resolution. It's the only technology that you can have equal slide thickness as the pixel size, meaning that in X, Y, and Z axis, the thickness it can be exactly the same. Okay, so that's very important to allow you to change any axis without distorting the images, and again, and allow you to just add every voxels using the 3D data set to calculate the volume. Okay, so if you know what your voxel size, which you determine by the slide thickness and your in-plane resolution, you know how many voxels, this voxel equals certain volume, and you just count number of voxels you have, and you get the volume. That's how we get the volume. So this is without any mathematical manipulation or presumption. Okay, so we talk about spatial resolution, voxel size. Now we talk about, very important, about temporal resolution. Heart move, as you can see. We need to freeze the heart. We need to have enough temporal resolution. And usually to freeze the heart, patient with regular heart rate, you need temporal resolution at least, ideally 40 or even 30. I think MRI is usually about 40 or 50. So you can see if you have low temporal resolution or temporal resolution is not enough, or the heart is moving a lot when you're imaging, you're going to have what we call motion artifact. Okay? The good thing is heart doesn't move into entire cardiac cycle. We have period where the heart is more quiet. Okay? And systole and mid-diastole. Everyone knows that for the cardiac cycle. Okay? And what determines the temporal resolution? It depends how long it takes for the X-ray tube to go around your body. Okay? Faster the entry rotation, better the temporal resolution. Since this is a circle, and and we have detected the other side, you don't need to rotate the entire 360 degrees. You only need to rotate 180, because you can kind of project back and get opposite of what you get, and that's complete the data set. So actual temporal resolution will be time for you to complete 180 degrees. Okay. And again, this is people have done this in the beginning of CT images to look at the length of systole and diastole as a function of the heart rate, meaning that the lower the heart rate, longer the diastolic period, right? And what remains constant is the systole. Okay, so diastole, that window decreased significantly with higher heart rate, with systolic doesn't get affected. Okay? That's why we're so vigilant about the heart rate, because that determines the image quality. And that's why when you have fast heart rate, we go for a little bit more sure period of end systolic imaging. Okay. This is just an example of different part of the cardiac cycle, can give you different images. And for low heart rate, 75% is the best. For high heart rate, anything over 70, I would say, and systolic is more reliable. And this is the gantry rotation speed of regular CT scanner. This is our 4 scanner working. Okay? So the new scanner, our 4 scanners go about single rotation in 250 milliseconds. Now there's a reason why they cover this, right? And you know, and obviously this is mechanical. I mean, you cannot make it faster, because if you make it faster, the thing will fly away, right? See the amount of a G they generate, over 35 G with a rotation of 250. So since we have 2 detectors, again, instead of going all around 180 degrees with single source, we can go around 90 degrees. So with Siemens scanner, dual source CT, the temporal resolution is the rotation time divided by 4. For any other single source scanner, it would be gantry rotation time divided by 2. Okay? So roughly, dual source CT scanner, the temporal resolution is about 65 milliseconds. And that's reasonable if your heart rate is around 60. If your heart rate more than 70 or 80, I mean, you're not really capturing what you think you capture. Okay, one word about contrast resolution that I mentioned earlier. Since we talk about the soft tissue, you cannot differentiate between blood and the, let's say, myocardium, for instance, right? So we have to use contrast, right? For instance, I showed this image earlier. If you have this picture only, I mean, this is a Lima graph, and this is a distal apex LAD. We give contrast. Now you can see this is the myocardium, this is LV cavity, and you have this native LAD, Lima coming from LAD, okay? And you can see the contrast, which is equivalent to the blood coming out from the Lima graph, okay? So we don't think it's like this, but that's why we use contrast, okay? Okay, so again, and contrast also allows us to characterize the plaque, either it's calcium or soft plaque, okay? Or lipid-rich plaque, depending, again, remember I say, if you have lipid-rich plaque, the Hounsfield unit is gonna be much lower than, let's say, fibrotic or calcium. So those are 3 major components we can more or less, and that's with the use of contrast. Okay, so how good is CT compared to other imaging modality in terms of spatial resolution, contrast resolution, or how contrast, you know, resolution? Think about how basically we call good image quality in a summary. Okay. So, not surprising, CT has the best spatial resolution, but has reasonable contrast resolution, and temporal resolution is the worst. Okay? MRI had not so good spatial resolution, but very good contrast. You know, you can see clearly the difference, right? You know, this is myocardium, this is cavity, and here you kind of, you don't know what that is, right? So this is CT images. And nuclear has the worst spatial resolution, very high contrast. You know, if you have, you can see clearly where the signal is and where there's no signal. And temporal resolution, echo is obviously the best, and MRI comes second, and CT lag behind. I think we can go through this quickly. Like most of the imaging modality, when we image the heart, we have to get it to the ECG, right? Because we need to know what we're seeing occurs in which part of the cardiac cycle. So this is the same with SPECT, so I'm not going to elaborate too much, right? Just give you an example. Every day, you probably, when you take care of the patient, you're going to see that patient had a PE protocol done with radiology. We non-gated, okay? If you're non-gated, you basically just scan the heart whenever. They don't care if it's in systole or diastole. So that's why you get motion like this, okay? Just to give you an example of, this is the same patient, had a CT PE rule out, done with GE scanner, and this is patient come back for a coronary CTA. Using gated, you can see the difference, right? You can see, now you can see the edges of the heart better, you can see the aorta better, and guess what? All these better images, because of the type of protocol we use, going to talk about later, use less radiation and less contrast. This is an example of patient with localized dissection, non-gated versus gated, okay? Okay, so other concept is important for us to understand when we scan the patient. We can do helical mode or sequential mode. Helical mode meaning the table is moving constantly when patient is being imaged. Sequential mode, when patient is being imaged, the table doesn't move. I'll show you some video later, okay? And all this is just you know, synonym, right? Retrospective, prospective, spiral, continuous versus step and shoot. Okay, so again, this is traditional, original CTA was acquired, continuous data acquisition. So you acquire, and retrospectively, you go back and pick up the faces and you assemble the images. That's called retrospective gating. And that's why you want to sample a lot just in case patient has arrhythmia. Okay? And therefore, the concept of pitch. Pitch is how much is the ratio between the table translation and the rotation slide width. So basically, it's the ratio how fast you're putting the patient through this compared to how thick it is, okay? So if you go table go very fast, you're gonna have higher pitch. Does that make sense? Okay. The other way around is if you have very skinny scanner, right? The pitch need to be higher. But if you have a very thick scanner, the pitch is not going to be as high. Okay. Okay. When you do prospective, so basically you are guessing when the next ROA going to be. So you kind of anticipate. So the computer analyzes the patient rhythm and decide, okay, it's relatively regular, and I think next R wave or next T wave is going to occur at a certain time, and that's when the imaging occurs. Okay, so and when that happens, the scanner doesn't move. And how much of heart you can image depending how wide the detector is. You know, if you have more rows of detector, you need less time to image, right? If you see only a small portion of it, it takes a longer time. So this is kind of schematic representation. So essentially, retrospective gating we use right now, mostly we need to see through the cardiac cycle, valve imaging, for instance, okay? For coronary, we don't really need retrospective images because where the coronary is in systole or diastole, it doesn't matter too much. But other type of imaging, doing helical scan, you could do it. You can move the table so fast, and you have two sources of X-ray. You can just image the heart for about 300 milliseconds, And this is what we call high pitch mode. So the table moves so fast that you can accomplish imaging the patient in a short period, in one single cardiac cycle. And that obviously, when the patient is exposed to the X-ray source for less time, you're going to have less radiation. So this is the main difference. This is the conventional spiral. Okay? The problem with the conventional spiral, one source CT, is if you go too fast, you're going to have data gap, right? Because if you move the patient too fast, there's no time for the X-ray to interact with the patient. But since we have two detectors, we compensate that, okay? So literally, you can scan the entire patient in about 2 seconds. So you can scan almost 60 to 70 centimeters per second. So you can, which is very useful for trauma patients, for instance. So this is just illustration of. Okay, so let me show you what the scanner do exactly. So all it took for the table to move, you acquire the entire images. So that's how fast you acquire the CT, right? And standard is very slow. So standard helical retrospective gating, the pitch is about 0.2, 0.3. With high pitch, it's 3. So we're talking about 10 times faster. Okay. Let me see, we can show you. So again, literally what you saw, how it took for that to rotate, for the table to move, that's what it took to actually image the patient. And needless to say, people are taking advantage of that, for instance. For image babies, here they put a doll in a rocking chair. And that's why we're talking the other day, you have very chaotic rhythm where you cannot really come up with a specific pattern. Sometimes you just scan the patient because the image, you acquire the image so quickly, you're going to have you have a good opportunity to land it in the phase of the cardiac cycle that heart is not moving as much, okay? So this is free breathing coronary CTA with flash technique. Patient in the ventilator, for instance, doesn't follow command. So I talk about great thing about dual source CT, right? Better temporal resolution, you can do high pitch, but the problem is you cannot have very wide detector, right? I mean, imagine you have two source, two detectors. There's only so many space in there, right? Our CT scanner, force scanner, has 96 slices, cover about 6 centimeters. Okay, so we need to go, in order for us to capture the whole heart, we need at least 3 rotations to cover the whole heart, okay? If you have one single source, you can make the detectors rows wider. And that's what Siemens, that's why GE and Toshiba does. They make detectors instead of 92 rows, they have 256 for GE and 320 for, and they both make about 16 centimeters, meaning that with single rotation, single heartbeat, you can capture the entire heart, okay? Okay, so this is the difference between one single beat and several beats. So this will be a traditional 64 slice CT. You have to capture, you have to stop and then take picture of the top of the heart. So by the time you get to the bottom of the heart, the time is different, right? Versus essentially just image the whole heart in a single beat. And needless to say, if you do one single rotation, the radiation is going to be less, okay? And as I mentioned earlier, also, the high pitch, if the pitch of a prospective gating or step and shoot is 1, and if you have a high pitch of more than 2, it's going to be about half of what prospective gating is. And again, there's some simple concept about detectors and number of slices. Okay, slices, number of detector is limited by the material we use, okay? Again, Siemens dual source scanner, we have 92 row detectors. GE has 256, and Toshiba has 320. But you can use electronic, you can split the row into 2 slices. And that's why you're going to hear Achelon 1640 slice CT, because from each detector you can generate, you do electronical moving the spot of what you image is. You can split each row detector into 2 slices. That's why Siemens advertised 192, I believe, slices, but in reality, we only have half of the rows, okay? So when you hear 640 slices, it sounds a lot, but in reality, I mean, it's the same, similar to, let's say, 256 slice of detector row of the GE. So the coverage is the same. Okay. Again, so the main advantage of single source wide detector CT is, again, remember that I showed you, the top part is going to image different in a different time point. So you're going to have different contrast, but compared to one single rotation, everything is uniform. So what happened here, exactly the same as what happened here, exactly the same time. And that's this is probably the best scanner for myocardial perfusion. Okay? All right, so dual source CT covers 6 centimeter, so we need 2 to 4 rotation for prospective scanning mode. It has a better temporal resolution because you only need to rotate 1/4 of the gantry rotation time. And you can do high helical flash mode, okay, which you only expose the heart to radiation for 270 milliseconds to 300. And wide detector CT is single source. You have a coverage of 16 centimeters, so you can do single heartbeat images, okay, most of the time. The temporal resolution is one single source. It's 256 or 320 detectors, so cannot rotate too fast. It's about 220 to 250 divided by 2 will be 110, right? So mostly you use prospective gating mode because there's no retrospective gating mode anymore with the single source wide detector CT for cardiac imaging, okay? Yeah, go ahead.
So for dual source CT, the coverage is not 16?
No, 6 centimeter. So that's only force. If you have the first generation dual source, the coverage is only 4 centimeter, like a 64 slice CT. Just because it is impossible to fit. Imagine you have 2 detector, 2 source, and 2 detector of 320. It would be a monstrosity. I don't think mechanically it's even possible, right? Okay, for the last 10 minutes, we're going to talk about what's coming. Right? The main pitfall of what we call conventional energy integrating detector that we currently use in our scanner is, remember I tell you that you generate electrons in the X-ray tube and interact with the anodes, and they generate X-ray, and X-ray goes through the patient and goes to the detector. Detector captures the photon, capture the light. The photodiode tube has to convert that light into electrical signals for you to reconstruct the images, okay? So all the electrical circuit gonna have noise, okay? So that's hinder the image quality, okay? And also with the regular CT scanner, if you have a higher energy photon, gonna generate more signal, right? Compared to a low energy photon. So the contribution is not equal. You could have one photon, higher energy, is gonna contribute more to the overall image than a lower energy photon, because sometimes low energy photon is important too, okay? And obviously, it cannot separate what energy the photon is coming. The photon is detecting, cannot tell what energy it is, okay? And also, when we talk about the detectors that I mentioned is made of ceramic and some type of composite material. Basically, there's a limit how thin you can make it, right? Whether if you use electronic pixel, you can reduce the size of the slice. So if you put all together and you can solve those problems, and this is what it will look like, the comparison between the regular CT scanner or energy integrating detector versus photon counting, okay? Let's follow this. You know, if you understand this, I think you learned something today. So you see this is, patient is here. This is a signal coming out of the patient, okay? So this is the detector that's facing the X-ray source, okay? You can see, I mean, you can make this only as the thinnest they have made is about 0.4 millimeter. Think about it, a material that's as thin as 0.4 millimeter, right? Which is pretty good already. So basically, the photon interact with this solid state scintillator detector, okay, and then convert the light into electrical signal, okay? So basically, you can consider this is the middle step, right? Versus photon counting CT, okay? So this is type of different material using electronical pixel. It directly convert into electrical signal. So you don't have to go through extra step. So with regular CT, you have to convert X-ray into light, into electrical signal. Here, you go from X-ray directly into electrical circuit current. So by eliminating this step, you eliminate the noise coming from the electrical circuit. And in addition, you don't need to use physical collimator, so you get better spatial resolution. So you know you're going to have better resolution, okay? So that's a main advantage from immediate advantage of photon counting CT. You're going to improve your image quality. The second major advantage is that now you are able to detect photon of different energy, okay? Because high energy so basically the signal you produce, okay? Before, with the regular CT, when you convert that, you lose that information. So you have a signal, you don't know what energy is producing it, okay? And in addition, as I mentioned earlier, high energy in regular CT contribute more because it generates more signal. With the photon counting CT, the contribution of high energy and low energy photon remain about the same. So it's a more representation of what actual tissue, right? Because tissue react differently to different energy. If you can separate them, you can do what we call spectral imaging. And you can potentially, from there, do material decomposition and do tissue characterization, right? Because each tissue has specific response or attenuation profile to different energy. Okay, but this is mostly for the future direction, future advances, okay? So this is what's available. It's easy gated, ultra high resolution. So currently our CT resolution is about 0.4, 0.5. With this, we can get down to 0.2, which is getting close to what the cath lab. Okay, cath lab could generate spatial resolution up to about 0.1 millimeter. So this is getting close to what you can get for the coronary angiogram, invasive coronary angiogram. And that's doing by direct conversion, direct conversion process, X-ray photon. Okay, and because of design, which I'm not engineering, so I'm not so familiar with it, it's more efficient, less noise, better image quality. So in plane resolution, probably not as good as what I put it here, mostly probably 0.2, but definitely better. And this is some of the example has been acquired. Okay, this is using the energy integrating CT. And this is using the photon counting CT. You can see much better edge detection, much better resolution, less blooming, okay? And because of the good resolution, you can remove the signal corresponding to calcium, because calcium reacts differently to different energy from a plaque, for instance, a soft plaque, right? So you can do a virtual extraction of calcium and get a better estimation of the true lumen stenosis, okay? And that could be used for stent. Okay, now for plaque characterization, you can see here this regular energy CT. You don't know if there's some soft plaque or not. With high energy, with ultra resolution, you can tell mostly just calcific plaque only, and that's confirmed by OCT, intracoronary OCT. And so we want to look beyond the coronary, right? I mean, it can be used for imaging prosthesis, in a sense, very high calcium, very high Hounsfield unit, and for stent. For large stent, you can have this degree of accuracy, okay? So exciting development, and hopefully we will learn more. But in summary, I don't need to repeat everything I just say. I mean, the idea here is for you to understand how the CT scan work, how do we get the images. And if you're interested, you have to go through each step, allows you to do certain thing to essentially to answer your question. And our goal as an imager is do what we call patient-tailored imaging. If you've gone through other imaging department, everything is protocol, right? You scan the patient for protocol. But each patient has different size, different indication, different age. We really would like you to have this concept of what the best scan mode and what parameter will get you the best images with less radiation to answer the clinical question, okay? And that's all I have today. Any question you have? Sir, any question? Good. So we're having the new scanner in about hopefully by the end of the year.